Okay, let's solve a solubility product question. In this example, they've told us that they've taken some solid silver chromate and added it to water at 25 degrees. Now, once it's dissolved, some solid remains at the bottom of the flask. That's how we know it's at equilibrium, that we've already reached the maximum amount that's dissolved. You're always going to have some solid and some ions in solution at equilibrium. Now, once it's at equilibrium, the silver ion concentration was measured to be 1.3 times 10 to the minus 4 molar. They'd like us to take this information and solve for the solubility product, the equilibrium constant for this dissolving process. Okay, if ever they want you to solve for the solubility product, the KSP, or if they give you the KSP, you want to do two things. You want to write the reaction where we show that solid slightly dissolving, and we want to write the KSP expression. So let me go ahead and write the dissolving process. That reaction is always shown as the following. You want to start with the solid. Our solid is the silver Ag2CrO4 in the solid state. This is going to dissolve a little bit. So we're going to go ahead and use some equilibrium arrows. Now, the part that dissolves a little bit will completely break up into its individual ions. When silver chromate dissolves, you're going to get 2 silver plus ions. So I'm going to write 2 Ag pluses in solution, aqueous, plus we're going to get 1 single chromate ion here, a CrO4 that has a 2 minus charge, and that's going to be in solution. Now that's the dissolving reaction. Let's go ahead and write the equilibrium expression for this reaction. We call that particular equilibrium constant, if a solid dissolves into individual ions, that equilibrium constant is called a KSP. SP, solubility product. So this is our solubility product that they want us to know. Now, when we write that equilibrium expression, remember it's always products raised to the powers equal to their coefficients divided by the reactants. However, in this case, our reactant is a solid. We leave out solids from our equilibrium expressions. So this equilibrium expression will simply have the silver ion concentration right here, Ag plus. That is going to be squared because we have a coefficient of 2 multiplied by the chromate ion concentration, our CrO4 2 minus, and that's simply to the first power. Now that is over nothing. We're going to leave out our solids. So that is the expression for our solubility product. Now, since we're doing an equilibrium expression, it's always good to make an ice table. We use ice tables for equilibrium reactions. So I'm going to do that up here. We have an initial, we have a change, then we have our values at equilibrium. Now, as for the initial, we're putting solid silver chromate in water. So initially, before this solid silver chromate dissolves, we don't have any silver ions and we don't have any chromate floating around. We're just using pure water here. Now, how much silver chromate? I have no idea. They didn't tell me, but that's okay. I don't actually need that information because I leave out the solids from my equilibrium expression. So I'm going to leave it out of my ice table as well. However, I do know that given some sort of a solid over here and no ions in solution yet, this reaction had to go forward to get to equilibrium. We have to get some concentration of silver plus and chromate. So I will know that I'm taking something away. How much? I don't know. Again, it's solid. But what I'm adding over here, I'm going to add some chromate over here. How much? A little. We're going to call it X. Well, if we add some chromate X over here, we're going to add twice that amount to the silver ion concentration because we have 2 silvers for every chromate. So I'm going to add 2x right here. Now, at equilibrium, again, I don't know what the equilibrium amount of my solid is, and I don't actually care right now. But at equilibrium, I know the chromate right here will be x, and the silver ion concentration is 2x. Well, if I plugged those into my equation right now as given, I'd have problems. I don't know the KSP. I don't know the silver if I just plug in 2x, and I don't know chromate x. There's just a lot of variables here. So this problem gives us one other key piece of information. It tells us that when we analyze the solution at equilibrium, we're talking about the E, we know the silver ion concentration. That silver ion concentration is 1.3 times 10 to the minus 4. So my silver right here, the amount of silver that I have at equilibrium, which is our 2x, is 1.3 times 10 to the minus 4 molar. Okay, so 2x, this silver amount, 2x is 1.3 times 10 to the minus 4. Well, I know for every 2 silvers that I gained, I only gained 1 chromate. This is a 2-to-1 ratio. So if I gained 1.3 times 10 to the minus 4th molar for silver, I have to gain half that amount for my chromate. We're going to take our 1.3 times 10 to the minus 4 and we're going to cut it in half or divide by 2. That number becomes 6.5 times 10 to the minus 5 molar. Now you know both these concentrations. You know the silver at equilibrium, you know the chromate at equilibrium. So I'm going to use those concentrations and plug them into my equilibrium expression. The KSP here will equal the silver value. At equilibrium, the silver value was 1.3 times 10 to the minus 4th. Now, we're going to go ahead and square that value. Because we have a coefficient of 2, we have to square it. And then the chromate ion concentration is the 6.5 times 10 to the minus 5. Now, if you go ahead and plug that all out on your calculator, you get an answer of 1.1 times 10 to the minus 12. No units associated with our equilibrium constants. That is fairly typical, this number, for a KSP. We have slightly soluble salts. You're going to see KSPs in the 10 to the negative something range. Some of them are actually quite small, and I hope that helps. Take care.